Hi guys, today I'm here to talk to you about some of the math-related concepts that you will see on the AP Bio exam. Some of them might feel like a flashback to elementary school, but bear with me because hopefully you'll be applying them in a more advanced way and also building on them with some new concepts. So let's start with some of those old ones: median, range, mode, and mean. Hopefully you know how to do all of these to begin with, but let's just review really quickly. Median, that would be the middle number. Range, it's from lowest to highest. Mode is the number that appears the most. And mean would be your average. So let's make up some random numbers that we can use. So we've got these two data sets now, very similar, with the exception of one extreme number in data set 2. Let's see if we can figure out mean, median, mode, and range, and see which one of these values would be most impacted by having one bizarre thing in there. So let's start at the bottom, work our way up from range. As you know, range is the smallest and the largest number. So the smallest number is right here, it's 3. Largest number is right here, it's 8. So for data set 1, I'm going to put 3 to 8 for our range. If we're taking a look at data set 2, 3 is still the smallest, but 500 is now the largest. So I'm going to put 3 to 500 for the range. If we're trying to find the mode is just the number that appears most frequently. In this case, why don't I raise these stars so we can focus in on the mode. In this data set, we only have one number that appears more than once, and that's 3. So 3 will be our mode because it appears most frequently. If we take a look at data set 2, what you see is that similarly, there is only one number that appears more than once. It appears most frequently, and it is 3. If we're trying to find the median, finding the median is basically trying to look for the middle. And so you knock out the biggest and knock out the smallest until you get to the middle. So let's try that. Biggest, smallest, and we're left with these two guys. As you know, if you have an even number of samples, you'll be left with two numbers in the middle, and you have to average them in order to find your median. 5 and 4, our average number is going to be 4.5. In order to find that average, to find that mean, you add them both up, in this case that's 9, divide by 2, because there's 2 samples, and you get 4.5. If we're dealing with the second data set, we take the largest, kick it out, bottom, kick it out, largest, smallest, and we're left with these two numbers, 7 and 4. It's not exactly the same as what we had before, but we're going to do the same process. We're finding the average of those two, we're finding the mean of those two, so we add them up, divide by the number of samples, which in this case is 2 samples. So 7 plus 4, it's 11. You divide by 2, because we have those 2 samples, and so we'll get 5.5. All right, so the last one we have to do is the mean. That I've cleaned up some of the stuff we've put up to help ourselves find median, mode, and range. We still have the same numbers in the same order. What we're going to do is add them up and divide by the number of samples we have. Those 2 steps will give us the mean. So if we add up data set 1, we'll get 30. If we add up data set 2, we will get 525. To find the mean, we just need to divide. To find the mean, we need to divide by the number of samples we have. In both cases, we have 6 samples. So I've written that out down here. We want the sum of everything divided by the number of samples. So 30 divided by 6. That will give us the mean of data set 1. And this actually works out to 5. So let's add that to our chart. Data set 1 has a mean of 5. If we check out data set 2, when we add all of that up, we got 525. We'll put that here. We still need to divide by the number of samples we had, which was in this case 6. And so what we're going to get then as our mean is actually a kind of large number, which is 87.5. So let's add that to our chart. When we are comparing these two data sets, one of the things that you'll notice is that a couple of these values aren't very different between them. The mode didn't change at all. The mode is very resistant to extreme numbers, right? Extremely large or extremely small numbers don't really upset the mode because that's just the thing that appears the most. The median is also much more resistant to change than what you would see with the mean, and the reason is because you knock out those extreme numbers right away. So although these are a little bit different, they're still reasonably close because the median, as I said, pretty resistant to change. The mean, however, the average number, you see a dramatic change just from the addition of one bizarre number. So one very large value or one very small value can really screw up where our mean belongs. The range, similarly, will be shifted quite significantly when you add in a very large or a very small number. All right, so there's a couple ways we can talk about the spread of our data. We talked about the range, and we looked at how much the mean would shift with just one weird, bizarre number. One of the things that you can use in order to talk about the spread outness of your data is something called standard deviation. How much does each point deviate from the mean, right? How far are things from the mean? How close is all of your collected information, and how far apart is all of your collected information? We'll talk about how to apply standard deviation in just a little bit. What I wanted to work through first is how to calculate it. So we've got a list of numbers. These are the numbers we have been using before, data set 1. And I've listed X at the top. X just represents whichever samples we have. So we have 6 different samples, and they're in this X column. What we're going to do first is we've got to average them, because you have to know the mean to find out how far everything deviates from the mean. We've already conveniently calculated this mean, but basically to calculate the mean, you add everything up, divide by the number of samples you have. To represent the mean, we're going to use the variable X with a bar over it. And that anything with a bar over it just means average. So we calculated this average to be 5. We added everything up, divided by the number of samples we have. The next order of business, if you ever forget, take a look at your equation sheet, because they give you an equation that, like the equation for the mean, looks kind of daunting. All right? It looks like there's a lot going on. But if we break it down, it actually clues you into every step you're supposed to take. What we're going to do is work our way from the inside here to the outside. We want to take these smaller pieces on the inside because they're easier to do first, and then build on them. So what you can see is we've got xi. Whenever the AP equation sheet uses I, they're talking about some individual point or the initial point. So here we've got our x's minus x bar. So the values we have minus the average value, which if you think about it, you're thinking about how far something deviates from the mean. It's going to be good to know how far each point is from the mean. And so that's what this is in here. We have our good friend the summation symbol that tells us eventually we're going to be adding stuff up. But before we do, we've got to pay attention to this squared symbol. So we find x minus x bar. We find the sample, the specific sample, minus the average. And then what we're going to do is we're going to square that number. The reason we square that number will become apparent in just a little bit, but basically it's because some stuff is going to be less than the average, some stuff is going to be more. The differences will add up to 0. But if you square a negative number, it's back to being positive again, and it's something we can use. So we've got the sample we have, the specific x, minus the average, square it, and then add all of them up. So let's do that step by step, and then we'll come back to the rest of this equation. So we have x minus x bar. The average, as we already know, is 5. So we know for this entire column, what we're going to be doing is taking the x, so why don't I write those down? and we're going to be subtracting the average. And the average in this case is 5. So minus 5, minus 5, minus 5, minus 5, minus 5, minus 5. Once we do the math out for those, what you can see, I'll make myself a new column just so we can keep everything clear. What you can see, now that all of these numbers have been done, is that we have positive numbers up here, negative numbers down here. If you haven't put your list of numbers in order, and you don't have to, but if you haven't done it, you won't get the separation of negative numbers and positive numbers. What this sort of reminds us of, though, is the fact that if we were just to straight up add these, the negative numbers add up to negative 5, the positive numbers add up to positive 5. So if we were to just add negative 5 and positive 5, we would have a 0, which is useless. So what we're going to do is we're going to square all these numbers so we get something that's nice and positive, and that we can actually then apply to figure out how spread out our data is. So x minus x bar. Next order of business is to square it. 3 squared is 9. 2 squared is 4. 0, 0, 1, 4, 4. Now that we have the squares, what we're going to do is find our sum. We need our sum of squares. So let's add these guys up. Once we add these up, what we are going to get is 22. And now we can look at the rest of this equation. We did this top half. We need to look now at n minus 1. If you recall from our discussion of mean, n is just the number of samples you have. So in this particular instance, how many samples did we have? We had 1, 2, 3, 4, 5, 6 samples. So what we're going to need to do in order to fill out this equation, let's put our square root sign just to keep that going. We found the top half of this equation already. We found the sum of squares, and that was 22, so I'll put that up here. The n, which we just counted, was 6. But we need to remember that unlike the average, we need to subtract 1 here, so it's 6 minus 1. So now that we've filled in the equation, all we have to do is the math. We have to take 22, divide it by 5, and then find the square root of that number. So if I give myself a little more space over here, the square root of 22 divided by 5 is actually the square root of 4.4. One of the things to be careful of, and one of the stupid errors that sometimes gets people, is jumping the gun and sort of taking the square root of part of this instead of the whole thing. You want to make sure that you do everything inside the square root sign first, and then lastly take your square root. So when we take the square root of 4.4, we get 2.1. 2.1 is going to be our standard deviation. It's going to be our value for S. So, what we're going to talk about now is why standard deviation is important. What standard deviation allows you to do. We've been able to calculate it, but it's useless if you don't know why you're doing what you're doing. Standard deviation, as you know, is how spread out your data is, right? Do you have most of your data points right by the mean, or are they sort of scattered? If we were looking at the heights of mice versus the heights of men, right, you would have a different spread. The mouse heights would be much closer to one another, and then the guys' heights would be much more different from one another. So how spread out you are is going to really matter. If you had two different people stand in front of you and there was a foot difference in their heights, you might not be terribly surprised. But if you had two mice in front of you and one was a foot taller than the other, you'd be very surprised, and also probably in the New York subway. All right? So basically, what we're going to use these standard deviations for is to tell us how spread out are your data points. If you care about what's happening to 99.7% of the population, most of all of those living mice, what you care about is standard deviation. Because if you take your mean and then you add or subtract your standard deviation, what you're going to be able to figure out is how many of the samples you've encompassed. If you take one standard deviation, basically, and add or subtract it from the mean, what you are taking care of is 68% of your population. So if you had 100 mice and you knew the average, you knew the standard deviation, you would have 68 of those 100 fall in this range. If you took 100 mice and you wanted a range that accounted for 95.4 if you want to be exact, percent of all of those mice, if you wanted to be like, you know what, I have the range of heights these mice are, and 95% of the time I'm going to be right. What you're going to use is 2 standard deviations. You're going to take your mean and you're going to add or subtract 2 standard deviations. If you want to be even more exact, if you want to account for even more of the mice, what you're going to use is 3 standard deviations, which will give you 99.7%. That is almost every single time you are right, right? So if you had 100 mice, you probably have 100 of them correct. Maybe you have one wrong, right? In that range. You'll be able to predict within that range very, very confidently the heights of those mice. This will matter a lot in biology because you want to be able to say, you know what, this drug works 99.7% of the time. If you're sick and someone comes to you and says, you know, this drug only works 68% of the time, all right, maybe we try it, maybe we don't. But if someone comes to you and says, this will work 99.7% of the time, you feel a lot more confident going into it. And you're a lot more likely to have a doctor prescribe it. So standard deviations can be quite important. So let's take a look. Now that we know 1 standard deviation, we're dealing with 68. 2 standard deviations, we've got 95% of the population, 95% of the time. And 3 standard deviations, we've got 99.7% of the time. But what does this plus minus business mean? Well, what we're going to do first is set up our mean. As you know, the mean from the data set we've been using was 5, so let me write those down. And then we're going to add or subtract the standard deviation. Let's start with 1 standard deviation. The standard deviation was 2.1. 5 minus 2.1 is going to give us 2.9. And then the top of our range is going to be 7.1, right? 5 plus 2.1. So between 2.9 and between 7.1, so within this range, you are going to account for 68% of the time. 68% of your samples will fall here. But what if we want to be more exact? What if we care about 95 or 95.4% of all of the samples? What we're going to do is we're going to take the 5, we're going to add or subtract 2 times the standard deviation, which is 2 times 2.1. If we can do the math out for ourselves, 2 times 2.1 is actually going to be 4.2, so let's update that. When you add, let's subtract first. 5 minus 4.2, we're going to get 0.8. And then the top of our range in this instance is going to be 5 plus 4.2, which becomes 9.2. Between 0.8 and 9.2, we'd have our answer 95% of the time. What if we want to be even more exact? We're going to add or subtract 3 times the standard deviation, 3 times 2.1. If we do the math, 3 times 2.1 is actually 6.3. So let's update that. 5 minus 6.3 is going to be negative 1.3. 5 plus 6.3 is going to give us 11.3. If we took the range of numbers between negative 1.3 and positive 11.3, we would account for almost every sample. All right? This is going to be very, very significant in deciding if a treatment works, if you have a normal height, or if you have something that's different from what you expect, right? Remember when we did our chi-squareds, we talked about how important it was to figure out if it's not what you expect, if something is abnormal, or if things start being abnormal a lot, then you know something is going on. So this is why standard deviation is important. So One of the ways that we can talk about that possible shift for each time you take new measurements, the difference that you see in the mean, is something we call standard error of the mean. And it requires you to understand that your spread outness, right, your standard deviation, might have some connection to how many samples you took. If you only took 3 samples, or if you only took 5 samples, you might not be terribly confident. You might be, but you might not be. All right, but if you took 1,000 samples, right, you'd be pretty sure your mean was close to where it was meant to be. Right, 3 or 4 samples, maybe your mean is off, you don't know. And so standard error of the mean is going to give you some sort of value that lets you have some of that assurance back. And so standard error of the mean, not to be confused, as you know, with scanning electron microscopy. It throws me every time I see this. So standard error of the mean, that's the one that you have on your equation sheet. It's not the only SEM abbreviation you'll have on AP Bio. Standard error of the mean, what we're going to take is the standard deviation, which we learned how to calculate, and divide it by the square root of n. As you know, n is the number of samples you have. If you have a huge value for n, 1,000, 1,000,000, right? This is going to be a really, really large denominator. Your standard error of the mean will be quite small, which will tell you, I am pretty sure the mean is here. If your standard error of the mean is large, you're not totally sure where the mean is. You're not totally sure if you have the right average.